Have you ever stopped to think about what's really going on inside a simple piece of metal? You know, like a spoon or a wire. Down at the microscopic level, it's just this wild, chaotic dance of electric charges. But, and here's the cool part, when things finally settle down, those charges snap into place following three simple, super powerful rules. And these rules, well, they shape our world in ways you probably never even realized. So let's dive in.
So here's the big question we're going to tackle. What happens if you take a chunk of metal and just stick it in an electric field? All of a sudden, there's this invisible force everywhere. So what do all those little charges inside the metal actually do? Where do they go? What's the end game here?
Well, the whole secret is right there in the name. It's a conductor. And what makes it conduct is that, unlike an insulator where electrons are pretty much locked down to their atoms, a conductor is just swimming in what we call free electrons. You can picture it like a sea of charge just sloshing around, not really belonging to any one atom. So when an electric field shows up and gives them a push, they're not stuck. They can actually move across the entire piece of metal.
And that very freedom, the ability to move wherever they want, leads us straight to our very first rule. Because once all that movement stops and the charges find their final resting places, the inside of that conductor becomes completely and totally calm, electrically speaking anyway.
Yeah, there's a fancy term for the stable state, electrostatic equilibrium. It's really just a way of saying that all the free charges have stopped moving around. And why have they stopped? Because all the pushes and pulls, all the forces on them, have perfectly balanced out. The three rules we're going to walk through are basically the blueprint for what this equilibrium state actually looks like.
Okay, so how does it get so calm in there? It all happens incredibly fast, but it follows a really logical sequence. First, an external field shows up and starts shoving those free electrons. They start to migrate, piling up on one side, which leaves the other side with a net positive charge. We call that polarization. But here's the really brilliant part. This new separation of charge, it creates its own electric field inside the metal, pointing in the exact opposite direction. And as more charges move, this internal field gets stronger and stronger, until, boom, it perfectly cancels out the original external field. And this is a great way to see it happen. On one side, you've got the cause, the charges separating. That's the polarization we just talked about. And on the other side, you see the effect. You've got the external field pushing in one direction, but that new induced field is pushing back with equal strength. So anywhere inside that conductor, they completely cancel each other out. It's like the charges are smart. They literally rearrange themselves to build their own internal shield. So here's the main takeaway, the big punchline for Rule 1. Once everything settles down into equilibrium, the net electric field anywhere inside that conductor is zero, period. And it has to be, right? Because if it wasn't zero, the charges would still feel a force, which means they'd still be moving. And if they're moving, you're not in equilibrium. It's a perfect self-correcting system. Okay, that makes sense. The inside is a totally field-free zone. But what if the conductor itself isn't neutral? What if we, say, dump a whole bunch of extra electrons onto it? It now has a net negative charge. So if the inside has to stay neutral, where in the world do all those extra electrons go?
And that leads us right into rule number 2. You got to remember, all those extra electrons are negatively charged, and they all repel each other. They're going to push and shove to get as far away from one another as possible. And where's the most space? Where can they spread out the most? Turns out, it's the outer surface.
Now, how do we know this for sure? Well, physicists have this really slick thought experiment that uses something called a Gaussian surface. It sounds complicated, but it's not. Just imagine drawing a bubble or a net, an imaginary boundary, just barely underneath the actual surface of the conductor. It's a tool that lets us peek inside, electrically speaking, and see what's going on.
And this is where Rule 1 comes back to help us out. We already established that the electric field inside the conductor is zero, right? Well, there's a super important principle in physics called Gauss's law, and it creates a direct link. It basically says if you have zero electric field passing through your imaginary net, then the total charge trapped inside that net must also be zero. Simple as that. No field, no net charge.
So think about it. We drew our imaginary boundary just inside the real surface. We know that inside that boundary, the net charge has to be zero. So if we dumped extra charge onto this conductor, where can it possibly go? It can't be inside our boundary. The only place left is on the outside of it, on the actual physical surface. It's the only logical place for it to be.
And this is not just a theory either. People actually tested this. Back in 1936, two scientists, Plimpton and Lawton, built this really ingenious setup. They took two metal spheres, one nestled inside the other. They'd charge up the outer sphere and then use a super-sensitive detector to see if even a whisper of that charge would ever sneak its way onto the inner sphere.
So what did they find? Zilch. Nada. Absolutely nothing. Their detector was so sensitive they could say with certainty that if any charge made it to the inside, it was less than 2 parts in a billion of the total. I mean, that's just incredible precision for the 1930s. And today, we've tested it to even crazier levels of accuracy. This is one of those things in physics that is just solid.
All right, so let's recap. Rule 1, the field inside is 0. Rule 2, any extra charge hangs out on the surface. That brings us to our third and final rule, which is all about what the electric field looks like right at the surface itself.
And the easiest way to get this one is to just think about what would happen if it weren't true. Let's pretend for a second the electric field comes out of the surface at some weird angle. Well, that means part of the field would be running sideways, parallel to the surface. But wait, where are all our free charges living? On the surface. So a sideways field would push them, and they'd start moving. And if charges are moving, what does that mean? We're not in equilibrium anymore?
So it's a simple contradiction. For the charges to be at rest, for the whole thing to be in equilibrium, there can't be any sideways force on them. And the only way to guarantee that is if the electric field points straight out, perfectly perpendicular to the surface at every single point. It's the only way to keep things stable.
Okay, so we've got our 3 rules. Field inside is 0, extra charge lives on the surface, field outside is perpendicular, so what? What's the big payoff here? Well, when you put these 3 rules together, you get something incredibly useful, a principle we rely on all the time, electrostatic shielding. Let's just quickly connect the dots. Rule 1 says the metal itself is a field-free zone, and Rule 2 says that if some external field shows up, all the drama, all the charge shuffling to cancel it out, happens on the outer surface. So what does that mean for a hollow space on the inside? It means that cavity is completely isolated. It's totally shielded from whatever electrical chaos is going on outside.
Just look at this. An external charge comes near, and the free electrons inside the conductor immediately rush to the outer surface to deal with it. They arrange themselves perfectly to cancel out that external field. And the result? The space inside, that cavity, stays completely pristine. It's a peaceful, field-free zone, totally unaware of the electrical storm raging just outside. And this protective shield has a name you've probably heard. It's a Faraday cage.
And once you know what to look for, you see this principle everywhere. The thick cable that brings internet or TV to your house, that's a coaxial cable, and it has a metal mesh inside acting as a shield. The metal box around your computer's guts, same thing. And yep, this is exactly why you're safe inside a car during a thunderstorm. The car's metal body is a Faraday cage. When lightning strikes, that immense charge flows right over the outer surface to the ground, leaving you perfectly safe and sound on the inside. So there you have it, 3 surprisingly simple rules that dictate how charges settle down in a piece of metal. But together they create this incredibly powerful shielding effect that is fundamental to so much of our technology. So the next time you see a metal case or a shielded wire, you'll know the elegant physics that's going on inside. Now that you know the rules, where else do you see them in action, silently protecting our world?